So today in class we came back and we're looking at electrons and where they reside. And so we started off with some takeaways, and then we get into talking about how we designate the location of electrons. We know from our previous studies that electrons are outside the nucleus, but exactly where we haven't quite defined yet. So there's a couple different ways that we can think about it. We can look at it from the perspective of the individual electrons and their mailing address, so to speak, where you can find a particular electron for the most part. But then we can look at it in a broader context of all the electrons in a given atom and where they are located or how they are distributed. And so we'll talk about each of those briefly, and we'll talk about the areas outside of the nucleus where we find these electrons and how we kind of subdivide those areas. The next couple of days, we'll spend more time on that broader context of, for all the electrons we've got, how do we distribute those? We'll look at those through the context of electron configurations, orbital diagrams, and you can see that for tomorrow there's an ed puzzle for you to consume that will get you ready for that lesson. There we go. So when we talk about where can we find individual electrons, we have what are called quantum numbers and quantum number sets. And basically what you have is each electron would have a set of 4 values that would designate a particular location, if you will, or an address for that electron. The first of those is what's referred to as the main energy level or the main electron shell. And that would be the whole number that you find at the beginning of each period. So period 1, 2, 3, 4, 5, 6, 7. Then if we take that main energy level and we subdivide it, and why do we need to subdivide it? Well, if you think back to the light experiment that we did when you looked at neon, for example, with the spectroscope, neon had 20 to 30 individual lines, colored lines, each one of those representing a different energy level. Well, when we looked at the Bohr model, which was those concentric rings, each of those rings represented one of the periods that we see on the periodic table. So there's well more than 7 energy levels. So there needed to be subdivisions of those, and that's where we get these sublevels. Those are designated with the letters S, P, D, and F. You don't have to worry about what the S, the P, the D, and the F stand for. Just know that those are the designations. Within those, there are individual compartments, if you will, and that's where your orbitals are at. So each of those orbitals, there's going to be a different number of them, depending on which type of sublevel you're talking about. And then within those orbitals, this is where you get down to the nitty-gritty details. You've got 2 electrons per orbital, and so electrons are both negatively charged. Like charges repel each other, so the way that you get 2 like charged particles to be able to coexist in the same physical space is basically you have to invert their polarities. If one's got its north pole facing up, the other one's north pole has to be facing down. So the concept of spin, if you think about it from the perspective of the Earth's core is made of molten iron. The Earth is spinning, and in the spinning of that molten iron core, it generates a magnetic field. We generally think of north up and south down. If you were to reverse the spin of the Earth, then the polarity of that magnetic field would reverse. And so if you have one negatively charged electron spinning clockwise and one spinning counterclockwise, their fields will be inverted and they'll be able to coexist somewhat peacefully in the same space. There'll still be some repulsion, but not as much as if they had parallel spins. So when we think about energy levels, remember that electrons are much like, if we think about the energy of an electron, think of it like potential energy of a book or something sitting on a table. There's a certain amount of energy that it has. Those electrons are arranged in different energy levels, and so when we move between energy levels, we have to increase or decrease that energy. Now, if we're going up the ladder, we have to lift our foot. There has to be energy applied to elevate ourselves. If we think about a book on a desk, to lift it, we're giving it greater distance to the ground, so therefore there's more potential energy. The closer you are, the lower you are, the closer you are to the nucleus, the less energy those electrons have, and that means that they're not as easily able to escape the attraction of the Coulombic attractive forces. So when we think about the different types of sublevels, again, they are designated S, P, D, and F. And so every single main energy level, 1, 2, 3, 4, 5, 6, 7, all of them are going to have an S sublevel. S sublevels, no matter if it's 1, 2, 3, 4, 5, 6, or 7, will always have one orbital capable of holding 2 electrons. P sublevels are first going to be found starting with the second main energy level and then every energy level thereafter. There are 3 orbitals within a P sublevel, and we'll take a closer look at those here in just a minute. P sublevels, no matter if it's 2p, 3p, 4p, 5p, doesn't matter, can hold a maximum of 6 electrons. D sublevels only start with the third main energy level. They have 5 orbitals, and if you're picking up on the pattern here, you might predict 10 electrons. And then finally, the highest energy of our sublevels, the F sublevels, the first one occurs in the 4th main energy level. These have 7 orbitals for a grand total of 14 electrons for the maximum total. Now, if you look at a periodic table, okay, when we think of a table, usually we think of something that is either perfectly square or rectangular, okay? And the periodic table itself does have some rectangular or squarish, characteristics to it, but it's kind of oddly shaped, okay? And so what I would ask you to do is for a moment, take a look at the periodic table. And the first thing I want you to do is picture taking helium from off its side and put it over right next to hydrogen, okay? And if you do that and you look at the periodic table and kind of step back and look at it, you should pick up that there are 4 distinct rectangular regions. A really narrow one on the left, kind of a squarish one on the far right, a big rectangle in the middle between those two, and then the long rectangle underneath, okay? These represent the different blocks of the periodic table. And if you take a moment and you count how wide are each of those blocks, the far left one, the real skinny one, that's 2 blocks wide. The square one on the right, 6 blocks wide. The transition metals in the center, 10 blocks wide. And the island, the long island underneath, 14 blocks wide. If those numbers sound familiar, 2, 6, 10, 14, they should, because they match the capacities of your sublevels, S, P, D, and F. So when we first started looking at the periodic table, if you recall, I told you I didn't want you to just take a blank periodic table and just fill it in for the heck of it. That's kind of pointless. It really doesn't give you much useful information. What's far more useful is understanding why the periodic table has this unique shape that it does. The reason it does is because, just like the game Chutes and Ladders, when you start at space number 1 and then you go to space number 2, 3, 4, 5, 6, well, our space numbers, those are our atomic numbers of our elements. If you follow them in order, each electron that gets added in, okay, is going to fill in these sublevels that match the sublevels of the blocks that are related to, the width of the columns that you've got, okay? And so you can wind your way down the table just following the atomic numbers, and you can get an indication of exactly which sublevel is being filled in next, okay? And for the most part, you can see that there's a relationship between the number that is in front of the sublevel letter and the row that it happens to be in. For instance, the 2S level is in that skinny S block in the second row. So the numbers match, which is nice. If we look at the P block, we see the same thing. The 2P level is in the second period, the second row. Okay, 3P is in the third row. Pretty straightforward. Until we get down here to the D block, and then we see a discrepancy. The 3D level is actually in the 4th row. If we keep looking, 4D is in the 5th row, 5D is in the 6th row, 6D is in the 7th row, we see that consistently the D sublevels are numbered one less than the row they're in. Okay? The F sublevels, if you follow the atomic numbers, okay, right here you have 56, and then the first one in the F block is 57. Well, if we were to take this whole long F block and put it up here where it actually belongs, it would sit in rows 6 and 7. So the 4F sublevel is being filled in, okay, when we're in the 6th row of the table. The 5F sublevel is in the 7th row. So again, we can see a pattern there. The number in front of the F is 2 less than the row of the periodic table that it sits in. So remembering those patterns, S and P's are numbered the same as the row you're in, D's are 1 less than the row you're in, and F's are 2 less than the row that you're in. Remembering that, you can identify the distribution of all the electrons in any element, from element number 1 to element 118, just by simply following, starting at the top and weaving your way down, following the atomic numbers, and filling in the sublevels as you go through the different blocks, numbering them, okay, in those ways that we just described. And that's, you'll get into that more in a future lesson. All right, so when we talk about energy sublevels, again, S sublevels, whether it's 1s, 2s, 3s, 4s, within any main energy level, the S is always the lowest energy, increasing as we go up to P, to D, and then finally to F. And probably the easiest way to think about that is the more electrons you have, the more crowded things are, and the more energy those electrons are going to have in order to have a stable, living arrangement, if you will. Kind of like if you're, the larger the family gathering is, chances are the more patience you might have to have as you go through that family gathering. All right, so when we talk about orbitals, again, orbitals are the areas in space around the nucleus where you're most likely to find an electron. Now, a lot of times we'll show these orbitals, and you can see here they look like fairly well-defined geometric structures, lobes, a sphere, that sort of thing. In reality, what those represent are the areas that have the highest probability of finding an electron in that given space. What's more accurate to represent the area of electrons is kind of a nebulous cloud-like appearance, and that refers to the electron density. The denser the cloud is, the more likely you are to find electrons in that space. No matter what type of orbital it is, SP, D, or F, whether it's the simple sphere or these complex ones down here for the Fs, all of those will only hold 2 electrons individually. They will only hold 2 electrons. So an S orbital, the first diagram you see here is more accurate of a representation of what the area or the field occupied by those 2 electrons would look like. And you can see, here towards the center, it's very dense. So there's much more likely of a chance to find an electron around here than out here. Okay, now, not right in the nucleus, because again, we know electrons aren't in the nucleus. So, this is forming the outside edges, okay, of what we would consider to be a sphere. And so when we look at this, it's important to remember it's not a hard shell like an eggshell, okay? Electrons don't follow a set track, okay? They have random motion. It's not even circular or elliptical necessarily. It's random motion at around a certain distance from the nucleus. If we take all of those points, it creates these shapes that we describe. So an s orbital is going to have a spherical shape around the nucleus. The only difference you can see between a 1s, a 2s, and a 3s is the size of that sphere, okay? If an atom had all 3 of these would be nested within each other. You'd have the 1s, then you have some blank space, then you have the 2s, then some blank space, then the 3s. And the blank space in between are areas where you don't have as high of a probability of finding the electrons. All right? Each s sublevel only has that 1 orbital and thus can only hold a total of 2 electrons. P orbitals, okay, again, you see this kind of nebulous electron density model shown here. And again, notice at the center of the nucleus, there's nothing there. Okay, again, we don't find electrons in the nucleus. They're always found outside the nucleus. Now, p orbitals, okay, we describe as having a dumbbell shape or a two-lobed shape. And those lobes for each of the three p sublevels that you have, or the three p orbitals that you have within a p sublevel, align themselves on each of the three axes. So that's where the designations px, py, and pz. It's talking about the orbitals that are aligned along said axis. Again, if we had a 2p versus a 3p versus a 4p, the only difference would be the size of the lobes on those p orbitals. The shape would still be the same. With Ds and Fs, they start to get a little more interesting looking. Ds aren't too bad, but Fs you'll see are another story. D orbitals tend to have 4 lobes on them, except for this last type here. And they're referred to as being flower or clover-like shape. You'll notice that unlike the p orbitals, those lobes do not lie directly on an axis, but rather between the axes. And so, for this first one, the lobes are on the zy plane. Okay, they don't extend out in this x-plane here, so that's why this is called the dyz orbital. And so if you just rotate which plane those 4 are in, you get these different designations. These start to get a little more intricate. We're not going to worry about those or even drawing these by my estimation. And again, size just gets larger as your main energy level gets larger. All right, so if these look complicated to you, then when we look at f orbitals, things get really interesting looking. And again, remember, each of these orbitals only holds 2 electrons. So these represent areas where we most likely to find those 2 electrons in these given orbitals. Okay. Again, just like a crowded family get-together, things get to be very complex. Seating arrangements might have to be a little more intricate, okay, to get everybody to get along well at the dinner table. You got 7 orbitals making up that F sublevel, and it's because of this complexity that really has the unique characteristics of your inner transition metals, those 2 rows, the lanthanides and the actinides. So what it comes down to is why elements behave the way that they do has to do with how are their electrons arranged. And there is a certain way, just like when you play Connect 4, you drop a piece in, it goes to the lowest energy level. You drop another one in the same column, it's going to go down, but it's not going to go down quite as far. And that board's going to fill up in a certain manner. Electrons are the same way. So what we've looked at today are the ways that we can designate where a given electron is, where a group of electrons are going to be, where they're going to go to into orbitals within sublevels, which make up main energy levels. And so what we'll look at in tomorrow's lesson is ways that we can represent those distributions through orbital energy level diagrams and eventually electron configurations. So thanks for watching. Please feel free to rewind and watch any section that you need. Have a good day.